Chapter 13, PLC logic and bit shift instructions. We have the ability to use NOT and or XOR, and then combinations of those to get the other logic functions. I have been doing this for better than 30 years, as everybody knows, and I have not one time ever wanted or needed to use any of those logic instructions. In 30 plus years, I have never seen it used by anybody else. I'm sure that somebody somewhere uses them, but very, very few and far between. So we're not going to spend a whole lot of time on it. When we get done today, though, we should be able to use NOT and or XOR, and then use the NOT instruction to create NAND, NOR, and XNOR. Okay, and then create ladder logic diagrams that use bit shift left and bit shift right. Be able to open up the data file bit dialog box so you can monitor the bit shift. You can actually watch the bits shift through the register. It's really cool to watch. And then, of course, reset. Allen Bradley, Slick, and Micrologics have the 4 logic gate instructions, NOT and or XOR. They're also available on control and compact logics. Let me zoom this for you. That's not too blurry, is it? You guys read it okay? Okay. NOT is the easiest one to grasp. All it does is flip the bit. So it flips a 0 to a 1 and a 1 to a 0. Okay, that's the whole thing. Bitwise and that does show the source A and B as hexadecimal. It's just an easy way for the computer to display it. It's called a bitwise AND because it is actually doing it at the bit level. Okay. So you have source A and source B. I never make that big enough. Okay, those are your possible combinations with 2 bits. It's A and B to get a 1. So if A or B is a 0, then your output's a 0. Okay. Only when they are both 1s do you get a 1 for the output. Okay, so let's take that as an example. What is A equal to in decimal? 10. Okay. What is 10 equal to in binary? Eight plus 2, right? Okay, so we got 4 A's on source A. So 1, 0, 1, 0. Let me move that closer together. So you guys thought you were going to be able to get away from numbering systems. No such luck, huh? Okay, and then source B, 00FF, what's 0? All zeros. Okay. So all zeros there, all zeros there. And what's F in decimal? Right? 15 and all ones, right? Okay, so we AND those together. Anything ANDed with a 0 is 0, right? So we can get rid of those right away. Anything ANDed with a 0 is a 0, so there's a 0 there, there's a 0 there, 0 there, and a 0 there. And then 1 ANDed with 1 is a 1. Right? All zeros, 8 plus 2, 8 plus 2. Okay, that's where they get the 00AA X for the answer there. Okay, that make sense? Ish? Okay. An inclusive OR is just OR. The fancy way of saying it. Talking about an OR, if either one of the bits is a 1, you get a 1 in the output. Okay. So we got there 5555. So 5 hex is 5 decimal. That's going to be 4 plus 1, right? Okay, so 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, and or that with FF00, I already know that all ones, all zeros. And again, anything ORed with a 1 is a 1. So these are all going to be 1s again. Anything ORed with a 1. And then both of them are 0. Get a 0 in the output. So 8 plus 4 plus 2 plus 1 is 15. F. 4 plus 1 is 5. FF55 hex. Okay. You are just far too enthusiastic for 8:15 in the morning. Now the XOR is a little different. For some reason, people have trouble wrapping their mind around XOR. Not sure why. If the bits are the same, no matter what they are, 0 out. If the bits are different, 1 out. Okay. Can you guys have a three-way switch set up in your house, you know, top and bottom of the stairs, different sides of a big room or whatever. That's an XOR. If both switches are up, the light is off. If both switches are down, the light is off. If it's one or the other, the light's on. Assuming the switches are installed correctly. If one of them's upside down, then, you know, that kind of goes out the window. Okay. So we got CE3C. We need to define CE3. Well, 3 is 3. What's C? Well, how do we get 12? What's E? How do we get 14? And then 3. 2 plus 1. Okay, so 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, and then 1, 1, 0, 0, right? Yeah. Okay. 6 hex is 6 decimal. We already know what E is. Well, we know F is all ones. 2 hex is 2 decimal. So 6 is going to be 0, 1, 1, 0. 4 plus 2, right? 0, 0, 1, 0. Okay. So 6 E F 2. Okay. Both zeros or both ones is 0. And then everything else is a 1, right? So 8 plus 4 is 12, which is C. All zeros is 0. No, 8 plus 2 is 10. 8 plus 4 is 12. And then 8 plus 4 plus 2 is 14. A0CE, is that right? Yep. Okay, so you see how that's working? Oops. Okay, again, not just flips the bit. 0 becomes 1, 1 becomes 0. Didn't I just do this? Okay. Getting ahead of myself. Okay, not or an invert, 1 to 0, 0 to 1, and is a logic low or a 0 if either of the bits is 0 or both. Or is a logic high if either bit or both is 1. XOR, logic high when one or the other is a 1, but not both. If you look at those instructions, B3 0 is the input, B3 1 is the output, and so on. It's that chart. Okay. The NAND is built by inverting an AND. So first thing you do is the bitwise AND, and then just knock whatever the result is. Okay. The NOR, you do a bitwise OR, and not the result. XNOR, you do an XOR, not the result. Status bits, status file 2. We do use some of this. There's a lot of stuff that is available in the status file. Some of it we use, some of it we don't. One thing that we're supposed to be using in every program is the overflow trap. You put that OTL at the very last instruction in your main program. S200 is the carry bit. So if you have a math function that has a carry of the 1, that bit will set. Overflow is if you try and calculate a number that won't fit in 16 bits. 0 is, of course, if the result is a 0, and then sign bit tells you whether it's positive or negative. If the sign bit is a 0, it's a positive number. If the sign bit is a 1, it's a negative number. Okay. Another status bit that we use frequently is the battery low. Controller will warn you when the battery gets low. You put that on, a status light or on your OIT. Have a banner pop up that says, hey, the battery's low, you need to change it. That kind of thing. You also have the free running clock, which those bits toggle at regular intervals. On the micrologics, it runs in microseconds. So bit 0 is on for 1 microsecond, off for 1 microsecond. Bit 2 is on for 2 microseconds, off for 2 microseconds. On for 4, off for 4, on for 8, off for 8, and so on. Those lower bits switch so fast that they're basically unusable. But if you get up around 12, 13, 14, then you can use that bit to toggle a light on and off, or a buzzer or something for an alarm. That way you don't have to burn 2 timers, time on and time off. So XOR instruction, output's high if one or the other is high. This is up to about here. So this first 9 bits, you look at it, 1 or 0 is a 1. 1 and 1 is a 0. 1 and 1 is a 0. So it's actually an exclusive OR. But when you get to here, 1 and 1 is a 1. So it kind of breaks that. Okay. Bit shift. This is what the lab is actually about today. Shift instructions often used to control display signs in a plant or outside. Flashing arrow display showing that one lane in the highway is closed due to construction can be constructed with a PLC bit shift instruction. Why in the world would you need to do a bit shift, turn on the light that says, hey, left center lane is closed? It's not going to move. That's what the bit shift is for, is to move the bits through your data file. One place that it is commonly used, though, is keeping track of things on a conveyor. Okay. So if you have a sensor at the start of your conveyor, and what are we sending down our conveyor? Bars of soap. Okay, like the way you think. Okay, so I have a sensor on the start of my conveyor, and as my bar of soap comes down, trigger this, give me an input. That's going to write a 1 into my data table. Okay. This type of application you'll be running on a timer, so every couple of seconds or whatever, you expect to see a bar of soap. So timer done, bit set, go look at the switch. There's another bar of soap there. I'm going to move that one down and bring another one into my register. Okay. Timer times out again, a couple of seconds later. Well, Lyle forgot to put his bar of soap on the line. So no bar of soap. That bit moves down the register, that bit moves down the register. Since there's no bar of soap, I bring in a 0. Next time there's a bar of soap there. So that bit moves down, that bit moves down. No bar of soap, bar of soap. And you can watch those bits propagate through the bit file. Basically, yeah. So that makes a whole lot more sense than lanes on a highway. This, I do not agree with. If you're doing bit shift, you are typically going to be keeping track of a single bit. Okay, if I move AA hex into bit file 0, bit file 30, the length is 4,306 or 43,604. The register is only 16 bits wide. So I'm not going to get anywhere near 43,000. Well, that would be the length of the file. There's only 256 possible. So 43,000 definitely ain't going to fit anyway. Okay. You're typically looking at a single bit. Matter of fact, on the shift instruction, it's looking at the first bit in that file. Okay, length of 7 You're going to have 0, 1, 2, 3, 4, 5, and 6. Okay, total of 7. So when whatever bit came in on bit 0 is shifted into position number 7, the instruction no longer cares about it. That makes sense? That would go into your unload bit, which we'll talk about here in just a sec. If you start at 0 and you're only interested in the first 7, as you're shifting through, you will see the bits continue through 8, 9, 10, down to 15. When it gets to 15, it'll drop off. It evaporates into the ether, I guess. The unload bit, though, is this /UL. When the bit in B306 moves into B307, that is the unload. That's what they're using to reset the bit file. Why they're using the reset there, I don't know, because that won't work. Well, no, that would work because they're looking at just the 0 bit. That'll work. And then get input 1, 2, resets the control register. Okay, when we get in the lab, this will make a whole lot more sense to you. Okay. So a bit shift left, when the shift is energized, shifts a bit to the left for every program scan. No, it doesn't. Bless you. It's not every program scan because we're talking millisecond program scans. It has to see a transition from false to true to do a shift. Okay. So best case scenario, it'll do it every other scan. I'll have to see a 0 or a false, a true, false, true in order to trigger the shift twice. Okay. Control register is used to hold status flags. PLCs use status flags in control registers to monitor and control the shift instruction. The control register in this case doesn't control anything. It just keeps track of where the shifter is at. Bit address for bit shift left, bits in the starting position. Number of bits that are shifted determines the length. Unload bit is where the last shifted bit exits. And then, of course, you have the length that determines how many bits it's interested in. Control register R6, 256 of them. Bit shift right is exactly the same as the left, only the bits go the opposite direction. Okay. There's a shift right. The other significant difference is where the start bit is. Since we're shifting bits to the right, we have to start at the top. Length of 6, 0, 1, 2, 3, 4, 5. Okay. And that's all of that.